So in this video we're going to go over elementary row operations, and these are going to be the operations that we're able to apply to matrices and preserve the solution sets. So we're accustomed to using algebra to solve systems of linear equations in two unknowns. We have learned in Algebra 1 and probably relearned in a pre-calc class the substitution and elimination methods for solving a system of equations. And in each of those cases there were actually elementary transformations that we were applying to those sets of equations in order to do the solution process. And what we want to do is identify that elementary row operations, which are the operations that we can apply to matrices in the solution process, are really the same transformations that we've been applying to systems of equations probably since 8th or 9th grade. So an elementary transformation, if you have a system of two equations, you can interchange them and it doesn't impact the solution set. In other words, if I have x plus 2y equals 9 and negative 2x plus y equals negative 3, there's no reason why I can't choose to write this equation second instead of first. In other words, I can exchange the order of those two equations, and the solution set, the intersection of the two lines, if it exists, should be the same as it was before I interchanged them. So if I take a system like this and I put it in its matrix form, 1, 2, 9, 1, 2, 9, and negative 2, 1, negative 3. Remember, in matrix form we just put the coefficients into the matrix, and this is an augmented matrix. An elementary row operation is to take two rows of a matrix and interchange them. So the 1, 2, 9 can become the bottom row, and the top row can become the negative 2, 1, negative 3. And if we do that, we shouldn't have impacted the solution set because we've done nothing more than change the order of the two equations. In our solution processes for systems, we've allowed ourselves to multiply both sides of an equation by a non-zero constant. So for example, if you wanted to use the elimination method to solve these two equations, what would you do? You'd multiply the second equation here by a 2. So I'd go 2 times x is 2x plus 2 times 2y is 4y equals 2 times 9 is 18. And then we would ditch this one and we would use this one to add to this guy, because negative 2x plus 2x is 0. It would put us in a position where we would be able to solve for y ultimately. So in matrix world, what we're going to say is, hey, it's okay to multiply the elements of a row by a non-zero constant, which really effectively is exactly what we do here when we're using the elimination method. So usually you say what transformation or row operation you're going to do. So usually I would say, hey, I'm going to take row 1 and interchange it with row 2, and then here I'm going to say I'm going to multiply row 2 times a factor of 2. So 2 times row 2, and if I do that, it's going to give me negative 2, 1, negative 3, and then 2 times row 2 is going to be 2 times 1 is 2, 2 times 2 is 4, 2 times 9 is 18, and I still have an augmented matrix, and you can see that the row 2 here is corresponding to this modified equation. So when we do solutions, we're changing the geometry of the problems, but if we have an intersection, all we're doing in a solution process is preserving the intersection. So we could here, if we wanted to use the elimination method, we would actually take this equation and add it to this one. So we'd get negative 2x plus 2x is no x. We'd get 0 x's here. Y plus 4y is 5y equals negative 3 plus 15. Sorry, negative 3 plus 18 is 15. Usually when you're doing a solution process, you don't keep the 0x, but effectively what we do is we add this to this, we get that 0, and then we throw this guy away. And we say now we're going to use this and this to find our solution. We've made a move that preserves the solution set. So here I could do the same thing. I could say, hey, I'm going to take row 1 and I'm going to add it to row 2 and replace row 2 with the result of that addition. -2, 1, -3. Keep row 1 the same, but replace row 2 with -2 plus 2 is 0, 1 plus 4 is 5, -3 plus 18 is 15. And I see here that this row corresponds to this equation right here, 5y equals 15. And of course, you know what you would usually do next if you were solving this system is you would actually multiply this equation by a fifth or divide both sides by 5. So if we multiplied both sides by a fifth, which is multiplying the elements of a row by a non-zero constant, the previous move we did is we added a multiple of the elements of one row to a corresponding row. You get 1y equals 3. Well, here what I could say is, hey, I'm going to take a fifth of row 2. So the result of doing 1/5 of row 2, it wouldn't impact the first row, but I would get 0, 1, and 3, corresponding to y equaling 3. So the gist of this video is to identify that when we're solving systems of equations, even in Algebra 1, Algebra 2, using the substitution and elimination methods that we learned back in high school, we were really applying transformations to the system. When we put the system into matrix form, we can still apply those same types of transformations that we did when we included the variables, but we can just apply the transformations to the matrices. And what you can see is you really don't need to know the variables. The variables don't need to be involved in this transformation process. So again, these are the big three elementary row operations. Interchange any two rows of a matrix. It's okay to do. You haven't impacted the solution set. Multiply any row by a non-zero constant. It's okay to do that. Add a multiple of the elements in one row to the corresponding row. You can add one row to another and replace the results with that addition. So that's the elementary row operations. Next video, we're going to see how to use elementary row operations to solve a system of equations.